Now it's my pleasure to introduce Kamatchi Gopalakrishnan from Juniper Networks. He's going to talk about differences between telecom and the financial network environment. Kamatchi, you don't have to use Victor's slide, though.
Okay. Good afternoon. I believe actually already here we all confused which technology to go for. Is it NTP or PTP or mixing both NTP and PTP or completely we find a new technology for our synchronization solution. To add spice to that, so I'm trying to bring in the one another technology or one another world of synchronization world, which is telecom. And but I'm not really trying to demoralize. Rather, I'm going to give a confidence that if we can achieve much stringent phase and time synchronization in case of telecom world, and why not we can get in more confined and enterprise world, right? Which is financial sector. Okay, basically the differences between financial and telecom network environment, specifically on timing and synchronization. Okay. So time sync basics, just to want to cover up, of course, different people already talked about the PTP and other aspect of it. Since I'm going to talk about a little bit on telecom side, so we wanted to know some of the minimum 3 technologies or when it comes to timing and synchronization. One is frequency synchronization, phase synchronization, and time synchronization. So frequency synchronization is something you use in the FDD technology, which is frequency division duplex. And phase synchronization typically we use in the TDD technology, which is time division duplex. And the time synchronization is the one typically we need in the financial sector where the absolute wall clock time is critical. So here just to really explain what is this terminologies and clocks so in case of frequency synchronization, all we're really looking for, 2 clocks are synchronized with respect to frequency. It's nothing but actually they are ticking at the same time interval or raising, the pulses are raising at the periodic interval of time t, and which is same for both the clocks. When it comes to phase synchronization, which is the middle one shown in the slide, where it's not only raising at the periodic time interval, but it's raising at the exact same moment, meaning if you look at the clock A and clock B, it's both raising at exactly the same moment. So it's basically aligned with respect to phase. So that's called, we call actually phase synchronization. When it comes to time synchronization, it's not just actually frequency and phase is synchronized, but the absolute wall clock time, clock A, if it says 1 o'clock in the afternoon, and clock B also should be saying same 1 o'clock in the afternoon, then we call it a time synchronization. So already there are different discussion about Doug talked about NTP, PTP, and IRIG technologies for synchronization point of view. So here to add some little bit more on the telecom side, some other technologies also we use. So of course, everyone talked about much on the GPS, and which is very critical, whether it's telecom or in the financial world. And NTP, again, I don't want to really create a controversial here. Of course, it's good for millisecond accuracy, and based on the implementations and stuff, maybe can go much better, but certainly not for very high precision, which is what we are going to talk about PTP. And the one another technology which is typically used in the telecom world is SONET SDH and Synchronous Ethernet. This one actually will provide you a very high frequency synchronization, but that's not sufficient for your financial world where you need absolute time of the day information. But we can add a spice onto that, actually, how you can use frequency to back up your, financial grandmaster or something. But directly that technology is not something very relevant for financial world, but it's very relevant in case of telecom world. Then certainly PTP, so precision timing protocol, which again we all talked about a lot here, and of course, like we are also trying to target that PTP is one of the candidate when it comes to high precision timing and synchronization. So this slide actually trying to cover, compare the requirements perspective between the telecom world and financial network, right? So we already talked about it's a frequency and phase is what you need in case of telecom network. You never bothered about the time of the day, whereas in the financial network it's basically a time of the day synchronization. UTC traceability is not a must for telecom world. Case by case, a arbitrary time source is also acceptable in the telecom world, right? Which is specifically if you talk about FDD technologies, like frequency sources need not be tracking back to the GPS, right? Or any UTC traceable requirement is not there. Whereas when it comes to financial services network, UTC traceability is must, and which is basically coming from ESMA, and again, in the US SEC point of view, it's a NIST traceability. Again, we had a lot of discussion about it's kind of one and same. When it comes to the synchronization requirements or accuracy, the telecom world is way stringent than what we are talking about in the financial world, right? In the telecom world, it starts from something under nanosecond synchronization accuracy to all the way to few microseconds, right? Certainly under nanosecond is used locationing services, E911 and stuff like that in telecom world. But when it comes to the financial network, it's really in an order of tens of hundreds of microsecond, right? So basically that can give you already if we are saying we are achieving the high precision requirement of 1.5 microsecond or something in the telecom world over hundreds of miles away from the grandmaster to the base station node, it shouldn't be a very difficult to achieve in the financial network, right? Of course, there are if and buts, but certainly from the technology perspective, using PTP, if we can achieve already on the telecom side, I think it's not a big deal to get into financial network. The another thing is actually when it comes to telecom, it's an operational requirement. When I say operational requirements, really the end application needs this phase and frequency synchronization. But at the same time, if you look at in the financial world, it's more of regulatory requirements apart from some of the operational requirements, right? So that's major requirements point of comparison between telecom and financial network. So we'll quickly talk about a little bit more detail on telecom and financial network, how these things are really works out, right? So now we saw that, in the previous slide, we looked at it actually the comparison of requirements, but here we are looking at the comparison of the network model itself, right? How would it look like in case of telecom and how would it look like in case of financial side? So telecom world, if you look at it, is typically a multi-operator environment. Core might be owned by some service provider, mobile backhaul may be completely different guy, operator, and the access may be the completely one another guy, right? But when it comes to FSI, financial network, mostly, I wouldn't say always, single network admin or single operator, but most of the time you have a confined network and you have a full control over that. So since actually it's a multi-operator network, in telecom world, it's very difficult, to pick and drive the network services. When I say network services or transport mechanisms, for example, whether you want to use IPv4 as a transport or IPv6 or directly over Ethernet, or you wanted to use MPLS or VPLS and stuff, basically the one operator need to rely on the other operator to make sure that that service is available end to end. But that's not really typically true in the financial because it's mostly you own the network. So that means you have a full leverage to what type of services, what type of network you want to come up with, and eventually you achieve your required phase and time synchronization. When it comes to telecom, actually, the downtime causes actually financial impact, right? Certainly, like, your base station going down, or like your cell phones are going down with signal or whatever, like roaming or whatever other services. But when it comes to financial, of course, you have a financial impact, then also you have a regulatory impact. So that's basically like much more critical if something you have a like failure or downtime in the financial network. So that's basically something like, makes a big difference between a telecom network failing for synchronization versus the financial network failing for synchronization. And the last part we already touched about, it's a timing is operational requirement, and here it's a regulatory requirement. So this particular slide to just show you, like, in the multi-operator world, how basically works in the telecom side. So if you look at it like the mobile core network, which basically holds the GM, it probably completely run by operator one. And then the backhaul, it's completely maybe another operator, which is, not really like related to operator one at all. And then the access network, it's completely another operator, operator three. So here, like if someone need to really achieve a phase synchronization of, end-to-end phase synchronization of 1.5 microsecond. I mean, this is not really, we are kidding, actually, like this is what we are already trying to achieve in the telecom world, and that is something possible. We are saying like, three different operators, and they are completely not really like interrelated, and they have so many other reasons to disagree with, starting from the transport mechanism, starting from the network services availability, whether QoS service or whatever, but there we are still trying to achieve the same not really same, much stringent 1.5 microsecond accuracy. And now we are talking about in the financial side, within a confined data center, why can't we achieve 100 microsecond, right? It's not a big deal. So this just quickly touch upon on how the operational requirement is. I'm not really go in detail because it may not be relevant for financial guys. But the basic idea is that why you need a frequency synchronization in the telecom world, right? So the simplest one application is whenever a cell phone roams from one cell site to the another cell site, right? It basically holds its frequency with which it's basically allocated on the base station one. For example, here, 2 cell sites, and each one is serviced by corresponding base stations, base station 1 and 2. And initially, the cell phone is associated to the cell site 1, which is base station 1, and it got allocated some frequency. And now you are really driving on your car, and you are really roaming to another cell site. So that means you are associating to the new site, new base station, and you don't want your call to be dropped. So you want successful roaming. So here, the stringent requirement, again, if you look at it, it's plus or minus 50 parts per billion, which translates to in time scale actually 50 nanosecond. So that's accuracy needed in case of telecom world, and certainly that's what we are already achieving in the telecom world. This slide just a little bit talks about the TDD and FDD technology. So it's basically in FDD, the cell phone and the base station will be using 2 different frequencies, so they basically transmit and receive at the same time. In the case of TDD, it's basically using a single frequency, so they have to share the time slots when to transmit and when not to transmit or receive. And that means that's where the phase synchronization becoming very critical. So that means if they step over each other, then certainly things are garbled between the base station and the cell phone. So these are different stringent requirements based on the type of applications you want to deploy in the telecom world. We talked about the parts per billion, and which is a frequency requirement, and LTA case. The LTE advanced network, we need somewhere between 0.5 microsecond to 1.5 microsecond, and E911 100 nanosecond synchronization accuracy. So now we'll just really shift on to the financial side, right? So as we talked before, it's most of time single operator domain, or you own the network. So that means you have full leverage to what technology to adapt in, and you have a full, way to really select your vendor, and measure your performance of the vendor or equipments or the devices that you wanted to get into your network, right? So that means like in a single operator environment like a financial network, it is much simpler to achieve what you want to achieve. So here one typical example shown here where synchronization flow model within the financial institution, how you really get the time to your end servers, right? Here in this model, like it's assumed everything PTP, no NTP in this one. So the end servers are really like running in their NIC card, like, a PTP client software. And you have like the leaf switches and spine switches. It's typical three-tier architecture in the financial network. And you do have a grandmasters. Either you want the grandmaster in your network or like you may get actually as a service from the external world. And you do have your gateway router here. So it's typically like a boundary clock at the spine and then a transparent clock in the leaf, and then finally your server sitting there, right? So there's one model where actually the synchronization is really actually flowing actually as an inline, meaning there is no separation between the data traffic and the PTP protocol exchange. Basically, both of them happening through the same set of boxes. And there is another model also like we proposed in some of the places where they don't want to upgrade their their leaf and spine switches for whatever cost and capex point of view. Then in that case, you can go the overlay model. The overlay model is like you completely skip your boundary clock and the spine and leaf nodes, but you really bring in actually a overlay model whereby the PTP packets are really like propagating a different network segment and eventually reaching to our servers. So now actually like why do we need, there are a lot of talk already happened, why we need time synchronization in financial. So first thing is, basic recommend is time legality. Right? So how do you prove that something happened before or after a certain time, right? That's a big question. So that's where like we're all trying to achieve this high accuracy time synchronization. So already Gil touched upon this, so I'm not going to spend more on this. So basically, MIFID and ESMA come up together like, the minimum requirements for synchronization recommends in the financial world. And so I'm not going to go more on that. So the last one is like profile comparison, right? So which I think like nobody touched, at least in the today's session. So when it comes to profile, basically what are profile? Profiles are subset of requirements derived from a 1588 standard. When I say profile, timing profiles, right? So we keep the mother spec actually as a 1588, IEEE 1588 spec, and from that, the profiles are derived. And what is the objective of the profile? It's targeted for a particular application to achieve the required synchronization goal, right? And most reliable and interoperable way. That's what, basically that's the main intention of coming up with the individual profile. People can, asking always like, oh, you have 1588 and why you really coming up with a different profile, one for, telecom and one for really like, enterprise and one for audio video bridging network and one for like IP broadcasting network, right? It's sometimes confusing. But the whole idea is that actually, the profile trying to really be explicit about what transport support supposed to be used and what mode of operation need to be exercised and what type of accuracy you need to achieve and how you really, validate your nodes and you design your network, right? So here it's listed a bunch of profiles like we are pretty much talking about the first two, telecom and enterprise. So quick comparison. So here, telecom profile, I pretty much took the, from the phase profile. Not really the frequency profile, because which is much stringent than the frequency profile. And in side by side comparing the enterprise profile, right? So it's PTP over Ethernet multicast. That's a telecom profile, which is standardized for the phase point of view. Of course, we do have like a partial timing support profile, which basically supports PTP over IPv4 transport. When it comes to enterprise, like we are talking about PTP over IPv4 or V6 multicast, right? And in telecom world, as I was talking about very earlier in the slide, like, we can do something, a mixed mode of operation, like both physical layer clocking, which is synchronous Ethernet, and PTP combined together to give a much higher stability and much higher holdover, whereas enterprise profile is kind of talking about a plain PTP mode of operation. Phase accuracy in microseconds, and your time of the day is what really key in enterprise profile, which is under microsecond as of today, but it can go much lesser. Fixed PTP packet rates, like you have to use that packet rate only, you don't really change it in case of telecom profile. Enterprise, you have a full luxury to really play with what rate you want to use it, and you come up with for your network design. And there is a separate alternate best master clock algorithm defined for the telecom, whereas the enterprise is using the default 1588 master clock algorithm. And one another thing is like no unicast negotiation. The purpose we use unicast negotiation, like, to negotiate the rates, packet rates. When I say packet rates, the PTP packet rates between the master and slave. Since in the telecom profile we fixed it, so we don't really allow separately, again, use unicast negotiation as a feature, whereas in the enterprise profile, if you need to, you can use the unicast negotiation, whereby, like, you can achieve like best rate you determine between the PTP master and slave, and use that rate to exchange packets and synchronize. Okay, so last slide. So already this is touched upon. So what are the real challenges in case of financial or telecom, right, to achieve the synchronization? The number one is packet delay variation. But there are like ways to really avoid packet delay variation, which is like you use completely AND path support, right? So every hop is boundary clocks or transparent clocks, and provided those boundary clocks and transparent clocks really support very good, synchronization accuracies, right? Then scaling, which is basically like how many PTP clients a particular boundary clock or a grandmaster can support, which really plays a major role in designing your network. Then number of hops between the grandmaster and your end slaves, which is typically very tough job, this particular attribute in the telecom world, but you have much control in the enterprise world. Generally, like it's a 3-tier architecture, but if you even going beyond that, you have full control of how to really, get the least path possible. Then precision performance monitoring, like already the FSM labs touched upon, and so which is very critical. It's not just you roll it in, but later you start monitoring and making sure that everything in place. And again, you can use the overlay model or inline synchronization flow. Inline synchronization flow may need really upgrade of all the boxes, or like at least minimum number of nodes in your network. Overlay model, maybe you don't need to upgrade, but you can use the separate network. Thank you.